All right, well, I think we'll get started. So welcome everyone to Science by Diverse Scientists. So today I'm very pleased to introduce Dr. Charles Brown, who comes to us. He's currently a postdoc and I believe Ford Foundation Fellow, right, at UC Berkeley, working in atomic physics. Dr. Brown did his bachelor's at the University of Minnesota and then his PhD at Yale. He's done a lot of work outside of his research, especially regarding underrepresentation in physics. And most recently, he was one of the leaders of the Black in Physics Week, which I'm sure some of you were aware of, and that seems like it was very successful. So, he's doing a lot of great work, and he's going to tell us, I think, about all of these sorts of things in his talk today. So welcome, Dr. Brown.
Thank you, Alex. Thanks for having me. I appreciate the invitation. I'm really excited about this program. I was mentioning before everybody came in that I think this is a really awesome program. Happy to be a part of it. And I wish it was a thing back when I was a college student in California many years ago. But okay. Sorry, one second. There we go. Okay, so today I will tell you about this quantum physicist's classical trajectory. I think in some ways this talk is a bit unconventional. I'm certainly going to tell you about some more standard research topics, which I'll actually start with, but I've tried to make this talk broad, at least scientifically, for the large audience, for the different level of the audience that's watching. But also I tried to make it very personal. So in half of the talk, I will tell you quite a bit about my personal experiences and sort of some particularly important details of my trajectory. But I'll start with the research first. So as Alex mentioned, I'm a postdoc at Berkeley. I work in Dan Semper-Kern's group. The group does many things, but my project is to study the behavior of ultra cold atoms in lattices made out of light. So in order to sort of motivate, there we go, what it is we're trying to accomplish, I want to tell you about geometric frustration and exotic states of matter. And so one way that you can describe what frustration is the conflicting interatomic forces that make unclear the lowest energy state of a system of particles. The lowest energy state being the state that any system tends to want to go to, right? And so a nice example of frustration can be shown just with an equilateral triangle, magnetic frustration. So imagine that I have this triangle here that you see, and at each vertex, I could have a spin, a particle would spin. Just know that it can be up or down, and know that the system minimizes its energy. That's what it wants to do by having neighboring spins anti-aligned, okay? So imagine at the bottom left corner, I put a spin up. In the bottom right corner, I put a spin down. Then the question is, what should the top spin be? You see that if it's spin up at the top, then the top and left spins interaction is not minimized. Or if the top spin is spin down, then the top and right spins energy is not minimized, right? This is a frustrated system. It becomes unclear what the lowest energy state of the system is. Something separate that you can look at, another way to study frustration is not by looking at magnetic frustration, so to speak, at least not magnetism associated with intrinsic angular momentum spin, but the orbital angular momentum, the motion at a given site on a lattice. So what I'm showing here is a cubic lattice made by these points. And at each one of these points, there can be these red arrows telling you about the orbital angular momentum. And it also turns out that there's a way to have these angular momentum vectors aligned such that it becomes unclear what the lowest energy state of this configuration is, okay? So to put it simply or clearly, our goal is to study the physics of orbital frustration, not quite like this, but orbital frustration. I'll say what it means and how it leads to exotic states of matter. And we do this by creating a Bose-Einstein condensate and putting it in a lattice that causes this orbital frustration. Okay, so there are two particularly interesting lattices, I would say, for looking at this. One is the Lieb lattice, and one is the Kagome lattice. And I'll point your attention to this one because this is the lattice that I work on. So what are some similarities and differences? You'll see that in both of these lattices are just a series of points where you can have particles, and I'll tell you more about lattices and geometry later. But at the end of the day, you see that there's some arrangement of particles that can be in this lattice. Here, it's sort of square. It is square. In the Kagome lattice, it's triangular-like. There's this parameter J that tells you about how atoms can hop from one site to another site. Okay, so while I guess at face value, these lattices look different, and they certainly have some different properties, they both sort of share these common properties that are particularly interesting for us, and they're shown in these images down here, which show band structure. So particles that are in lattices have band structure. Band structure tells you about the available energy states that the particles can have. And depending on if that band structure is flat, or if it's curved, or if it's curved in a particular way, all this has a very strong bearing on what the properties of the system is, or the particles in the lattice, or in a solid state system, the physical properties of the material. Okay, so again, both of these lattices have these interesting properties. One, you see they have a flat band, and this is really interesting for us. This is a location where the energy of the particles in the lattice actually don't change with their momentum in the lattice. That's a very unique thing. Both lattices have this flat band, but there are also other interesting regions. There are these regions here that have something called Van Hove singularities, which is this peculiar region where the number of available states explode. All right. Then there are these other interesting regions here called Dirac points. And I would say that this has been studied a lot in graphene. Graphene has Dirac points where electrons that flow in graphene near Dirac points, they behave like massless relativistic particles. This has been a very interesting source of research here. Okay. So I guess I wanted to, sort of make sure I'm being clear about what we're trying to do and make sure I'm clear about what these terms mean. So when I say orbital, I'm referring to atomic motion. And when I say geometric frustration, I'm talking about a large number of ground states in the lattice, okay? So here, again, it's our Kagome lattice. The Kagome lattice is formed by this series of equilateral triangles that share a vertex, okay? And for any, there's so much interesting physics in the Kagome lattice. For any of the experts that may be watching, there are even these interesting states of circulation where you can begin to study vorticity and other interesting properties of atoms and lattices and things like this. Okay, but again, I keep on talking about band structure. So here I've plotted for you the band structure of the Kagome lattice. So what you'll notice here, so this doesn't look like the three-dimensional rendering I showed you. I'm giving you these 1D slices, but I'll just point out that this is a band here. This is another band. This is a flat band. This is another band, okay? And again, these bands tell you about the available energy states of the particles. And the labeling here doesn't matter so much. These are just different ways to label the momentum of particles inside the lattice. But again, you'll notice that this band is very, very flat. This is how we get frustration in our system. We see that the available energies have very, very little dependence, if any, on the momentum of the particles in the lattice. Okay, this is how we generate frustration in our system. Okay, and so let me start by sort of at the most fundamental level that's appropriate for here, and I'll sort of build up through all the relevant parts of our experiment. So I should say something quick about the difference between bosons and fermions. So they have strikingly different behavior if you try to trap them and you put them at 0 Kelvin, the lowest temperature allowable, right? So if I try to put a collection of bosons like these here in a harmonic trap where the potential that the particles fill varies quadratically with position, the bosons are happy to crowd up all on the lowest energy state. The lowest energy state being shown by these lines here, right? So this kind of potential has a series of energy states. They're equally spaced and they're labeled by these ends over here. And again, bosons are unique because they are happy to crowd on top of each other in the lowest energy state. This is how you make exotic states of matter like a Bose-Einstein condensate, which I'll mention a little bit later. That's very different than fermions, for example, which do not want to do this. We know of this from the Pauli exclusion principle, where even at zero temperature, the fermions, they don't all want to be in the same state, and they'll sort of stack up through these energy levels until they're at an energy level that associates with the highest energy of these fermions. It's the Fermi level. So in our system, we use the bosonic isotope, rubidium-87, to make a Bose-Einstein condensate by doing exactly this. We force these bosons to crowd up on each other, a lot of them. We make them very, very cold. Okay, so I want to tell you a bit more about Bose-Einstein condensates because they're amazing. And they're a really integral part of how we do the physics that we do. So when you're thinking about a state of matter like Bose-Einstein condensate, it's useful to think about the de Broglie wavelength. The Broglie wavelength describes the wave-like behavior of matter. I have the expression for you here. This is the de Broglie wavelength. It is inversely proportional to mass and temperature. So you have a large mass, you expect this de Broglie wavelength to go down. If the temperature is large, you expect the de Broglie wavelength to go down. I have a de Broglie wavelength, so do you. It's tiny. You can check that by plugging some numbers in here. And this is the reason why we don't do weird wave-like things, right? Because of the fact that decoherence from the environment makes all the sort of wacky quantum waveness go away. But it's there, right? All matter has this de Broglie wavelength. And it turns out that if you have a system where the temperature is low enough, the sort of volume, V per particle, can be less than the cube of the de Broglie wavelength. This is a situation where the wave function that describes the different atoms, they all sort of overlap with each other, okay? And I'm showing an image here taken from NIST and Gila, CU Boulder, where they make a Bose-Einstein condensate. This is actually an image of the velocity distribution, I guess, of the gas. And as you go from left to right, the gas is actually getting colder, where the distribution is peaking at zero velocity, right? So they have this sample of cold gas trapped, and they cool it until it condenses into a new phase of matter called a Bose-Einstein condensate, associated with being the lowest energy level of the trap, sort of all behaving in a similar way, all having the same energy state, almost acting like a giant atom. So when you learn quantum mechanics, you would start to think that, you could describe something like this with the Schrodinger equation, right? The Schrodinger equation tells you about how a particle might evolve under some influence of a potential V, right? So the first term is the kinetic energy. The second term is the potential. This is the thing that's applying the outside forces. And psi is the state that you care about. And you can take psi and you can extract, you can use it to extract observables like position or momentum or energy, et cetera, right? And this is just given the total energy. But for a Bose-Einstein condensate, that is an interacting system of quantum particles, you actually need to add another term, this interaction term, which now makes this the Gross-Patevsky equation or the nonlinear Schrodinger equation. You'll see that not just psi appears here, but psi squared. This is actually the density, right? So you have a density-dependent interaction term. And so that tells you that in our experiments, the density of the gas, of the Bose-Einstein condensate is going to play an important role in how the system evolves. Okay, and so I like to include as many pictures as I can. Here's a picture of a Bose-Einstein condensate taken from our lab. This is about 50,000 atoms in the BEC. The temperature is about 50 nanokelvin. And yeah, as far as we know, this is the coldest state of matter in the universe, right? The tiny, tiny fractions above absolute zero. Okay, so let me say a bit about lattices. So I've already mentioned the Kagome lattice. We study the Kagome lattice because it has a flat band, and flat bands allow us to should allow us to study frustration. Right? So generally, a lattice is a periodic set of points that has some set of symmetries. Here's a square lattice. So One thing that these lattices that I'm showing you have is translation symmetry. So I can draw a box, for example, around this point here, and I can translate this box up and down, left and right, and I can use it to replicate this lattice, right? So this lattice has this translation symmetry. You also see that this lattice has a 90-degree rotation symmetry. If I rotate the whole lattice by 90 degrees, it looks the same, right? There's also a triangular lattice that has translation symmetry, and it has a 60-degree rotation symmetry. There's a Kagome lattice. Again, this is our special lattice. Also has translation symmetry and a 60-degree rotation symmetry. Okay, and again, you know, I know I'm sort of belaboring some points, but that's because I'm going to show you some data, and I, you know, want to try to make some points clear. Particles and lattices have band structure, and so what I'm showing you here is a calculation of band structure for a one-dimensional lattice. Here's what the band structure would look like if there was no confinement of particles to the lattice. This means the potential energy associated with lattice is 0, right? No confinement. What you see is the energy on the vertical axis depends how you would expect it to depend on the parameter on the horizontal axis, the momentum, right? So generally you would expect the kinetic energy to go like momentum squared. And so this is what we're seeing. We see that the energy of these different parabola or these curves, they are quadratic in the momentum, right? And so when you take a lattice and you actually turn on the confinement, when you make the lattice non-zero, you see that these bands are actually formed. Here's the lowest band, here's the next lowest band, here's the next lowest band. And the particles in the lattice actually can't have energies that are in these gaps. So it can't have energy in this white region or this white region either. Okay, so this is an important property of lattices. Now, I'm telling you a lot about lattices, but how do we actually make them in the lab? Well, we do it using laser lights and making use of some wave phenomena that we are probably familiar with. And so if you take a look at this, this GIF here, I'm showing you the combination of the red traveling wave and the blue traveling wave. They travel in opposite directions, and when you add them together, they make a standing wave. Right? And we can do exactly this with lasers in the lab, where we just shine two lasers pointed at each other. Okay. And if you take a zoom in the region where they overlap, and you look at the time average of the electric field intensity, the square of the Bloch curve, what you get is this fixed waveform, right? Which actually makes a series of local potential minima for the atoms, and we could put atoms in there. Right? So these are my bosons. I can load my bosons into this one-dimensional optical lattice that has this perfect spacing that's set by the wavelength of the light. And there you go. I have a one-dimensional crystal right here, essentially. And I can do this in multiple dimensions. So I can do this in two dimensions and make a 2D lattice, or 3 dimensions and make a 3D lattice. Okay, and so to make an optical Kagome lattice, we do this in 2 dimensions, and we actually use 6 laser beams. So we use some green laser beams. They're all at 120 degrees relative to each other, and we overlap them with another combination of 3 beams, the ones that I'm showing in red here, but these are infrared. And if you look at the potential energy landscape that the atoms fill at the intersection, you get the Kagome lattice, depending on how you control the polarization of the electric field polarization of the light. But this is a Kagome lattice. This is the actual potential energy landscape that the atoms see. The dark regions are the low points in the potential energy. The white regions are the high points. And this is just rotated. This is just rotated relative to the images that I showed you earlier. So, oops, here we go. This is the top equilateral triangle that shares a vertex with this triangle, sharing a vertex with this triangle, sharing a vertex with this triangle. Okay, and so on. So this is the Kagome lattice. Awesome. So let me tell you about some of our experimental results. In this experiment, is a recent paper that we published in Physical Review Letters. We take a rubidium BEC, much like the one that I showed you in the image earlier, and we apply a laser to it. So we apply the center of the laser here, this darker region, offset from the BEC. So we're looking in the top view. And what this does is create a dipole force that draws the BEC towards the center of the laser where the electric field intensity is highest. But we just pulse this laser on. And so what this does is it gives the BEC some acceleration. And so we can move the BEC up to some speed, some velocity V that we control before we turn on the lattice, before we shine on all the lasers that form the optical Kagome lattice. And in this way, we can control which of the different energy bands we put the atoms into. Okay, so here's something fun I wanted to show, and here's some actual data along with it. So we take our data here by looking at images, by doing image analysis of the BEC after it goes into the lattice and interacts with the lattice. Okay, and so here on the top panel, I'm showing these predictions of what we call diffraction images. So as I told you earlier, BECs are wave-like. They behave like waves. And so just like light can diffract from objects, so do BECs. And what we take are images of a BEC diffracting from the lattice. Okay, so here is what we predict the diffraction image to look like when the BEC is given 0 momentum. So it's just sitting there with 0 momentum, and we turn on the lattice and we turn it off. This is the diffraction image that we expect, and this is what we see, right? This is another diffraction image, but this is where we've given the BEC a small velocity, okay? Small it means something in particular, but I won't get into that yet. And we see something that agrees well with what we predict. Okay, so this is a picture of us actually giving the BEC a significantly larger velocity before we turn on the lattice and putting it into one of the higher up energy bands that has a very different diffraction image. And we see that there's decent agreement between these two. And this is us putting the BEC to even a higher energy band, right? And again, there's sort of decent agreement. Where's my mouse? There we go. Between these two images. So this is just to show that, you know, this is the kind of data that we look at, and we can extract important physical properties from it to analyze our data, and that we have a good handle of the experimental sequence. We sort of know, like, oh yes, we're giving it approximately this velocity, and we're putting the atoms in this band or this other band. Okay, so let's get to the sort of more meatier part and the most important, I would say, data in this paper. It's this plot. So there's something called the Hellman-Feynman theorem, this expression here, that allows us to extract this expression here. Okay, so I'm going to tell you what this is. This is a very general result of quantum mechanics. This is also a general result, but something very relevant for us. So it turns out that the group velocity, this is the velocity of the particles in the lattice, can be calculated from looking at the derivative of momentum. That's what this this del sub q is, the derivative in momentum space of the energy bands. Okay, this is equivalent to the average velocity of the average velocity. Right, this is the expectation value of momentum over mass. This is the average velocity. This is the velocity of the particles in the lattice, and we can extract this velocity by looking at the slope of the energy bands. And how we actually get the group velocity is by looking at the center of mass of this image, of the images here. Right? So if we look at the center of mass of the image, from that we can extract the slope of the energy bands. Right? So here I'm plotting the slope of the energy bands as a function of the atom's momentum in the lattice. Okay. So here, this is the atoms in the lowest energy band, right? Or maybe the first Brillouin zone. This is the atoms in the third band. This is the one that's supposed to be flat. This is the atoms in the fourth band. All right, so I spent a long time telling you that the Kagome lattice is amazing and interesting because it has a flat band. Well, if the energy band is flat, and I'm looking at the derivative of something flat, then I should get 0, right? But we see here that we're actually not measuring 0. So 0's down here, our data is in blue, right? And within the error bars that we can generate, there's a significant offset, like a noticeable offset from 0. So what's going on here? Well, let me point you to the solid black line. The solid black line comes from the Gross-Vitebsky equation, which involves interactions between particles. So I mentioned to you that the Bose-Einstein condensate is a system of interacting quantum particles. It has that extra term in the equation that describes how it evolves. And when you actually use that additional interaction term in the, and you turn the Schrodinger equation into the Gross-Vitebsky equation, what you predict for the group velocity agrees much better with the data that we measure, as opposed to the result on the dashed line that you get from normal band theory, which doesn't know about interactions. Okay. So let me say a little bit more about this. I just have a couple more plots to talk about. I'm going to completely switch gears. So what we've noticed is that the band structure is renormalized. The potential energy landscape that the atoms see has actually been augmented due to the presence of interactions. And so when you think about it this way, perhaps it's not so surprising that we are not seeing a flat band, right? A flat energy band is a property of the Kagome lattice. But if this interaction energy, this interaction between atoms, make the atoms effectively see a different lattice, it's not the Kagome lattice, well then generally perhaps you wouldn't expect it to have this flat band. Okay, and so there's a bunch of not interesting stuff that comes out of this like nonlinear equation, right? So the Gross-Vitebsky is this, the Gross-Vitebsky equation is this interesting nonlinear Schrodinger equation, and nonlinearities in differential equations always make for interesting stuff. Certainly makes for some interesting physics, especially as it relates to symmetry breaking in lattices. But I won't say too much about that here. However, I will point out this plot. So in this plot, we're showing the amount of atoms in these different sites, right? So these are the sites of this is called the unit cell, and the unit cell has some number of sites, and it's the unit cell that you can transfer around to generate your lattice if the lattice has translation symmetry. So I showed you that earlier with the square lattice. And so each one of the 4 sites, each one of the really 3 sites, but 4 sites in the Kagome lattice can have some population. And what we see as a function of how strong we make one of the set of lasers that make the Kagome lattice. So this is to say, as a function of the geometry of the lattice, because if we change the strength of one of the sets of lasers that make the lattice relative to the other, it changes the geometry. What we see is that as we change the lattice geometry, the population, say in site A, the amount of atoms in site A changes, the amount of atoms in site D changes, B and C changes. Right? So we expect that there is some significant change in the number of atoms, and so some significant change in the way that the lattice physically looks to the atoms as you change the lattice geometry. And again, the interaction term is significant here. It's strong enough to distort the local geometry of the lattice, right? So again, this is sort of more information regarding why we don't see the flat band that we had thought we would see, and it's because of these interactions. Okay, so more proof that interactions are playing a role. Here, this is the last data I'm going to show you. This is some plots of the group velocity again. This is the slope of the energy band, which we extract from the center of mass of diffraction images like these. The blue is our data. The dashed line is the sort of usual theory for calculating properties of band structure that don't know about interactions. And the black solid curve is a result from solving the Gross-Vitebsky equation on the lattice. And again, we see that the Gross-Vitebsky equation does a pretty decent job of predicting what we expect to see. Okay, so this plot I'm showing you here is the group velocity changing as a function of the lattice geometry. This is effectively the lattice geometry, right? So we're saying that the slope of the energy bands, the flatness of the energy band, this is in around the third band that's supposed to be flat. We're seeing that the flatness changes as we change the lattice geometry. Okay, and again, I'm telling you that this is happening because of density, right? And so what I'm showing you here is the group velocity, right, which is the slope of the energy band, the sort of flatness as we change the density. And so I showed you in the gross potential equation, the density term, the interaction term is proportional to density. So I change the density, I change the strength of the interactions. And we see as I increase the strength of the interactions, the group velocity goes up, the band becomes less flat, right? So again, this is just all more proof that interactions between the atoms cause the band structure to change, because the effective lattice, the effective potential energy landscape that the atoms see changes as well. Okay, so I'm going to switch gears. I told you a lot of very, very cool stuff about some quantum mechanics, how we use quantum mechanics, studying BCs and optical lattices. But I want to tell you a story about how I got to where I am. Okay, so I'm going to start from high school, actually. I've gone through a very, very windy path, and I wasn't always happy that it was so windy, but I'm happy about that now, because it's offered me a great deal of perspective that I feel like is incredibly useful. Okay, so here's a broad overview of my path. I'm from Las Vegas. I was raised there. My mom's from there. We've had some generations from Las Vegas, actually. From Las Vegas, I went to this really, really small town in California, Northern California, called Susanville. I think the population was like 6,000 people. On Friday nights, people went to Walmart to hang out. I mean, it was that kind of place. It's a wild transition coming from Las Vegas. From Susanville, I went back to Las Vegas. From Las Vegas, I went to Minnesota, not straight to the University of Minnesota, actually, which I'll mention. I eventually went to the University of Minnesota, where I got my bachelor's degree. Then I did grad school at Yale. Now I'm a postdoc at Berkeley. And what's next? Well, I don't know. I can tell you that I very much want to be a faculty member. I feel very strongly about academia. I want to be a part of shepherding it into the future. So hopefully, within the next few years, I'll see if I can find a faculty job. We'll see what happens. Let's start from high school. This is me. So I'm going to show you a lot of personal stuff, a lot of personal pictures of me and all these things. So get ready for a ride. I was an athlete for a long time. This is me here looking goofy in the center. I went to Las Vegas High School, sort of random public school in Las Vegas. It turned out that I loved wrestling, but I didn't really want to do it initially. I remember feeling very strongly that wrestling was just really silly things. Like, oh, all these guys running around in tights. Like, what's going on? This is so silly. And I had lost a bet, and in losing my bet, I had to go to a wrestling practice, try out for the wrestling team, and then I fell in love with wrestling. And this was a shock to me. I ended up wrestling for 3 years, and I ended up becoming a really, really good wrestler. So that was surprising. But throughout all of this, I knew that I wanted to do STEM, and I wanted to go to college, but I was sort of unsure of what exactly I wanted to do. I also wanted to point out that I was a first-generation college student. My mom has always placed an incredible amount of importance on education. It's been an important driver for me. And I think that, when I was in high school, there was definitely a strong push to, go to college and like do what I'm passionate about and do STEM. But again, it was sort of unclear what the right ways to do that were. There's a lot of stuff that, we sort of didn't know or we didn't have information about, that made the whole situation a lot more complicated than it needed to be. But hey, it worked out all right. But like I said, I loved wrestling, and I graduated high school a little early, and I got an offer to wrestle in college, so I did that. So this is me on my college wrestling team. This is me over here. So I ended up wrestling at a community college that was a really strong feeder into D1 wrestling programs, Division I wrestling programs. There's a long heritage of producing some really great wrestlers. And I was like, okay, I have this opportunity to go and wrestle there. I, was young, just graduated college, graduated high school. I'm like, oh yeah, I want to go on an adventure. So I went to California and I wrestled for a couple of years. I still wanted to do STEM, and just I think this sort of thing is important. I think that it's easier for younger people to see someone like myself or other people, someone like Alex, and be like, oh, things must have gone really easily for you. You must have, cruised through everything, blah, blah, blah. I didn't. So I took calculus my first or second semester. I'm having a hard time remembering. And I didn't do well. I didn't do well because I could basically not stay awake. We had 2-a-day wrestling practices. And this guy here, he was the older guy who did not want me to take his spot. And so he made sure that I felt every wrestling practice, every workout, every day. And I had a hard time adjusting to a college wrestling program workout regimen. It was much, much more intense than high school. And just, trying to just be awake during, an 8 a.m. calculus class was very difficult, but I figured it out eventually. It was just an adjustment. I was supposed to actually go and wrestle at the University of Oregon. That was my big break, right? I did well when I was at Lassen in Susanville, and I was going to wrestle for the Ducks. But their wrestling program got cut through rebalancing funds for sports from Title IX. So that was a big surprise. All right, thought I was going to Oregon. That didn't happen. I don't remember what this acronym stands for, IGETC. It's some sort of transfer curriculum agreement, at least it was in the past, between California community colleges and the UC system. And so I had at one point planned to transfer over to Berkeley, but that didn't work out because there was this clause that said, if I remember, there was a clause that said, like, there could be some course exemptions in the transfer curriculum agreement if you couldn't find that course or particular course at a college within like 100-mile radius of you. And that was the case. There was actually 2 courses that I could not find close to where I was. But despite the fact that I technically had this exemption, I don't know, it didn't work out. So I didn't transfer to Cal. And I was sort of at a bit of a loss for what to do at the time, because the plans that the two big plans that I had made that I was really, really gung-ho about just didn't work out. And so at this point, I decided to end my wrestling career and just focus on STEM 100%. And let me say that I met a lifelong friend along the way. This guy here, Dr. Anthony Clay, is now a research chemist at the Army Research Lab and one of my best friends. Okay, so like I said, I had this abrupt stop in my plan, this abrupt hurdle, this obstacle. And so I actually ended up going back home, and I moved back in with my mom. And I was going to a local college here, the College of Southern Nevada, another community college. And I was working a lot. I was working around 30 hours a week and going to school full time. This was very, very intense. I don't recommend it if you can get away with not doing it. I understand some people have to, I had to. So while I was doing this, I was taking multivariable calculus, differential equations, physics, those sorts of courses. And I actually had a really bad teacher who really mistreated her students. She was a brilliant person. And it was very, very clear. And unfortunately, she was very demeaning. And if you got things wrong, she would scold you and actually demean you in front of the class and in front of other students. And it affected me very strongly, and a lot of other students. And a lot of students that were interested in physics got turned away or were convinced that they didn't have what it takes, that they didn't have the skills to do physics. And somehow that didn't deter me. I mean, it certainly almost did. I really thought about okay, maybe this isn't for me. But this is around the point where, I was already passionate about STEM, but I was okay, I think physics, this is what I want to do. I was finding out that among the science classes and engineering classes that I was taking, the stuff that excited me the most was everything about sort of why things are the way they are and how they work at more fundamental levels. So I was starting to get really excited about physics here. Okay, and so next, after a year of being back home with my mom, working all these hours and going to college full time, I applied to the University of Minnesota, where I eventually got my bachelor's degree. But the first time I applied, I didn't get in. And that's because there was one course that I needed in order to transfer there. And I just really thought that it was going to be okay, and it wasn't okay. So I had to go to a community college there. I was really dead set on moving to Minnesota. My best friend Anthony, the one I showed you in the picture, he was from Minnesota originally, and we were going to initially try to go to Minnesota, the University of Minnesota, together. Turns out that he changed his plans. He actually decided to keep on wrestling. He ended up getting a nice scholarship to a private university in North Dakota, and he finished his bachelor's there. But I didn't want to wrestle anymore, so I eventually went to the University of Minnesota. But in order to do that, I had to go to a community college just for a single semester to get a course that would transfer to the university. That was Normandale Community College. It's actually a really great community college. And that was also school number 3. So I've been to a lot of higher education institutes along the way. That was number 3. Okay, so when I got to Minnesota, I sort of feel like I was back on my path. Whatever that path was, I was on it. You know, historically, I was a strong student, but my experience at the University of Minnesota was really intense. I think that throughout the years up to that point, I didn't quite develop the study skills that I needed, or like the study habits that I needed to do well at Minnesota. So the first semester was really, really difficult. I didn't do nearly as well as I had wanted to, but I figured it out. I bounced back, and everything worked out nicely. I wanted to highlight that, you know, I was going to these small schools before this. You know, these are community colleges that have these small classes and everything. And all of a sudden, I find myself in a 200-person third semester physics class, doing integrals and things like that in a huge auditorium. Right, I was one of 2 Black people. There was me, the physics major, and there was a math major, Vincent. Right, and that was it. But this is when I started to fall in love with quantum mechanics. So at the very end of this course, we had an intro about quantum physics, which I thought was the coolest thing. And then I took a course from Jim Kakalios. Some of the faculty on the call might know who he is. He's very involved in lots of like physics teaching. He also wrote a popular book called The Physics of Superheroes, which is really cool. But he's a really great teacher, and he taught my quantum physics course. And after I took quantum with him, I was like, oh yeah, this is what I have to do. It was very clear to me. Yeah, so while I was at Minnesota, I got involved with the Society of Physics Students. I became president, vice president, and then president, and really completely revamped the group. And we even won the outstanding chapter from National SPS in 2012. Right, so the group had sort of died, and I feel like I've always felt like, as far as I can remember since I was an adult, like outreach is important. And so we did really cool outreach programs like this family fun fair, right? We have this huge center called Kaufman Memorial, and we had a bunch of families. Like there were definitely the first time we did it, something like 400 or 500 people that came, families of all different walks of life with their children. They come into this huge room with all these different physics demos where they can like do hands-on stuff. They can touch things, they can explore, they can do science themselves, and they can talk to a bunch of really, you know, bright-eyed physics students about them. This was a really, really awesome program, and one of the best things I think we did. We also did things like nuclear science merit badges for Boy Scouts, so they can come to SPS at the University of Minnesota and get their nuclear science merit badges. It was through a whole day of programming, doing different science and giving talks and stuff. And then we also did a combination of demos and talks with inner city students in Minneapolis. At the time, I also co-founded this group called the Nikola Tesla Patent Producers, NTP Squared. This is a group of some of the founding members. This is our attempt to make a Tesla coil back here, which eventually worked, but it was harder to build than we thought. Here's me. I don't know why I look like this, but I wanted to share a special picture with you all. You know, we really wanted to take the science knowledge that we were learning in the classroom. We wanted to do something for the greater good. We all felt really passionate about it. And so we started building different projects. And it, you know, this group actually, it ballooned into something really large, changed the name to Tesla Works. And this student group at Minnesota ended up annually getting tens of thousands of dollars in funding. It really turned into something that we couldn't have initially imagined, but it was a really, really great experience. This is also around the time when I sort of realized, like, oh, like I have the ability to like do science stuff and be successful, and I can make things happen. And sort of before this time, I didn't have a strong sense of this. But after these experiences, I started to sort of find my voice in a way, I guess. And we even started a company. A group of us started a company, and we competed in business competition. So 3M, the materials company, if you use Scotch tape or the 3M strips, right? 3M, they have a business competition called the Minnesota Cup, and we were division finalists in it. We didn't go super far, but it was really incredible experience. Oh, I'm completely forgetting to show you my pictures. So this is us in NTP squared. This is the group of us that started the company. And this final picture I wanted to show you here. 6 years after I graduated from high school, I graduated with honors in physics and a minor in math at the University of Minnesota. This is me on the Jumbotron in the auditorium at the University of Minnesota with my cool stole. Is that called stole? I think it's called stole. Maybe not. Something like that. Anyway, and my honors medal. It was a really incredible experience. Again, I was a first generation college student. Can't tell you how happy my mom was. And I can't even, I've always wanted to be a scientist, but I can't tell you that I honestly always thought that like this would really come to fruition. So this is a really important time in my life. And for any of you who may have seen my Physics Today piece that came out back in July, I was very open about a lot of experiences I've had with anti-Blackness and racism. And this was just after the previous summer where I was doing a research program at UChicago. And one night I was assaulted by police for no other reasons than being Black. And I can tell you honestly that at the time this happened, I didn't know if I was going to make it through this event. I thought I was maybe going to die in that moment. And so having this moment of graduating and being the first in my family to do so was a really powerful experience for me. Okay, and so next I'm gonna move on to grad school. I have a bit of time left. Maybe I'm going a little too slow, so I might try to pick it up. I went to Yale to do a PhD, right? Couldn't believe it. Not only did I get my bachelor's degree, I was the first one to do so, but now I'm at this, fancy Ivy League place. It was pretty wild, just to say it frankly. I joined Jack Harris's group, which is largely a quantum optics or optomechanics group. The group is mostly interested in studying the quantum behavior of objects that, at least when you first learn quantum mechanics, you learn they're too big to behave quantumly. Turns out, quantum mechanically, and turns out that there's a huge caveat there, and studying macroscopic quantum mechanics is an incredibly interesting field of research. Okay, here I just wanted to show a picture of me. I joined the grad club rugby team. So we had a rugby team and we would play rugby against the other Ivies, and this was a ton of fun. I just kind of wanted to show this because it's an important thing to me. Exercise is really critical for me. And I actually feel really strongly that it makes me a better physicist. I think when I'm working out and exercising regularly, I think much more clearly. So even if I didn't only care about my health, right? Health is super important. And I just wanted to be really good at physics. Exercise does both of those things. Also, I want to point out that I met a very important woman in my first year. This is me and her. Who I will eventually marry. I'll show you another picture there. But at some point in grad school, I started these really cool experiments where I was studying superfluid liquid helium. And I see I left something out. I studied superfluid liquid helium inside of optical cavities. So optical cavities are essentially two mirrors that face each other. Light can bounce back and forth in between. The light gets trapped there. We fill this volume up with superfluid liquid helium. Superfluid is another interesting state of matter. And we could look at how the light that's trapped between the two mirrors interacted with density fluctuations in the superfluid, right? So this is what I started working on. And I won an NSF graduate research fellowship. But of course, not everything is good. And I'm telling you about my experiences. I had a lot of people who weren't happy about this, that felt that I didn't deserve it. I was told several times that I only won this because I was Black. And this was sort of indicative of a lot of experiences that I had at Yale. I had my fair share of racism. I dealt with my fair share of racism at the University of Minnesota, but it was unique at Yale. It was unique in that it was much more intense and just persistent. Let me also say that the classes, the combination of classes and teaching and research, it was all very, very intense. So all of a sudden I'm a first year at Yale, and I have to teach students, and I have to take these difficult classes myself. And I go to the lab 10 hours a week and break stuff. That was essentially the experience. Right? I mentioned here that I dealt with an immense amount of racism on campus. And the point that I wanted to mention here is that I for a while, I really did question my belonging in physics. And I seriously considered leaving because I was nearly convinced that I wasn't up to snuff. And this sort of thing, unfortunately, happens to lots of students, lots of Black students, lots of other students of color, lots of other marginalized students, especially marginalized students who have intersectional identities that identifies multiple marginalized groups. Right? This can be super, super complicated, and sometimes these environments can be incredibly hostile. And I like to make this point that I think it just became clear that many people couldn't accept that I was part of the intellectual community at Yale, and for that reason, life was very difficult for me for years. But community was important, and I wish I learned this earlier in life or in grad school. But finding a community of scholars who looked like me, who were okay with the fact that I was Black, who didn't think less of me because I was Black, was super important. Here's a picture of what we call Black Lunch. This is unfortunately a large collection of the Black STEM students in the Ph.D. program at Yale back in, what was this? This was probably 2016, 2017, maybe. Just an interesting fact. You were looking at a large number of the Black men in the grad school. I know in 2015, I was one of 25 Black men across the whole graduate school of arts and sciences at Yale. And I think the number of Black women are about the same, right? So there's a very, very small number of Black grad students at Yale and an even smaller number of Black STEM students. Okay, so there's Black Lunch, super important. Oh, this is the picture I wanted to show. This is the important woman who I eventually married, and you'll see a lot of the same faces that appeared in earlier pictures. I'll point out this one. This is Dr. Anthony Clagan, the chemist at ARL, their Army Research Lab. This picture is really important. This is me at the National Society of Black Physicists annual conference, and this experience really changed my life. I went to the NSBP conference at the end of my second year, I think, or during my second year. This is the time, yeah, the beginning, end of my second year. This is the time where I like really, really needed to be there. And I don't know if grad school would have worked out for me if it had not gone. It was a time where the racism that I was dealing with was really getting to me, and I was really wanting to leave. And the only thing that was really holding me, anchoring me to campus was the woman who became my wife. But when I went to the National Society of Black Physicists conference and I saw literally hundreds of Black physicists, very successful at all levels, I found it so incredibly inspiring. And I knew I wanted to be a part of the organization. And so I was actually able to, in 2016, at least between these years, 2016 to 2018, I was the national student representative for the organization. So I was the liaison between Black physics students and the leadership of the organization, just trying to make sure that the needs of the students were being heard and worked on by the board. So this is me, obviously, and this is the one of the previous presidents, Dr. Renee Horton, who's a staff engineer at NASA, actually. Also co-founder of the Yale League of Black Scientists. So this is a group of, this is one of the co-founders here. This is me, a grad student, and then one of the other co-founders is my wife, Lindsay. We started this group, the Yale League of Black Scientists, which was meant to build community among the Black STEM students, Black PhD STEM students, and also to like aid in our own professional development. And we wanted to inspire the next generation. So we did a lot of work with really awesome kids like this from the local New Haven community, going to their schools, talking to them, sitting down, eating with them, telling them about our lives and doing science with them, right? So yeah, eventually I won a 4 dissertation fellowship. I built this really awesome brand new experiment where instead of studying superfluid helium in optical cavities, I levitated a drop of superfluid helium in vacuum and made that drop the optical cavity itself, and also this interesting vibrating element where the hope is to study the quantum mechanics of the interactions between the light that's stored in the drop and the drop's vibrations itself. Okay, and I got my PhD, so this is after my PhD defense. This is my mom in the my mom in the audience being as happy as can be. That was my story up to then. I also wanted to show you this really cool video. I love condensed matter physics. I'm an atomic physicist now, but I mean, I'm also a condensed matter physicist. I use atomic physics techniques to study condensed matter. You don't get to see superfluid helium too often, so let me show you this cool video that I took in grad school. So we're looking into this chamber that I built. This surface here is a right-angled prism mirror, and so is this one. And so as we look into the screen, the reflection that we see in these mirrors is actually what's in this central region, okay? And so this is a chamber. We're looking through a puddle of superfluid helium right now. I'm gonna aggressively pump on it. It's gonna release a mist. I'm gonna grow the superfluid drop in its trap. This is a short video. I think it's really fun. So here's a superfluid drop. We grew it in this trap. It uses an incredibly powerful magnetic field. It's like 15 Tesla. It's like 5 times stronger than an MRI magnet. And I don't know if you've seen MRIs will like rip screwdrivers out of your hand from feet away. So this is an incredibly powerful magnet. And we use it to levitate this cool state of matter called a superfluid that has these crazy properties. Like, you know, if you put superfluid helium in a little vessel, a little container, it will siphon itself up the walls and run out and drip out of the container until it's empty. Superfluid helium also is like, people are familiar with superconductors, is like a superconductor of flow. So if you put superfluid helium in a bucket and you rotate the bucket, actually, let me say it this way. If you take liquid helium that's not superfluid and you rotate it so that the superfluid has this rigid body rotation, and then you cool it down to become superfluid, it will retain its rotation, albeit in a different form, but it will rotate indefinitely, right? It flows with zero friction. That's what makes it superfluid. Really, really incredible state of matter. Okay, so this is the last thing I wanted to tell you about my path. And so I know that I'm, if Alex, is it okay if I take just a few more minutes? I know I'm a bit over, I apologize.
Yeah, no, I think that's fine. Yeah.
Great, thank you. So yeah, I think throughout my path, I made this uncomfortable realization, and that was that there were missing persons in STEM. You know, I would definitely, it's the case that Black physicists are very poorly represented among physicists, and this is incredibly apparent to me because I'm Black, and you know, for much of my life, the fact that I'm Black has defined a lot of the experiences that I have. So I wanted to show this picture. This is a picture from one of the important physics conferences in my subfield of physics in grad school. In this photo, there's about 150 people. There's one Black person, one Latino person. The rest are white and East Asian, specifically East Asian. And this sort of thing is common. Right? Here's another photo at a different conference. There's actually another Black person here, which is quite uncommon. Here's another picture from a different conference, another important conference in my field. There's again another Black person, a different one, right? But it's just me and him. Okay. And even this photo, this is my incoming graduate school cohort. So this is me back in 2013, looking extra cute and young. Don't even recognize that guy anymore. But this is sort of an interesting picture, and it's very telling. One thing is, this is Brooke Russell. Brooke Russell's actually, she's the first Black woman to get her PhD from Yale Physics in like the 150 years that the program has existed. And there's only been about 8 of us total. Yeah, I think there's been about 8 of us total. So you're seeing like 25% of the people to get their PhDs from Yale Physics, Black people to get their PhDs from Yale Physics in 150 years. I mean, this is really wild, right? The representation problems are really strange. This isn't just a one-off with Yale. A lot of programs just have never graduated Black people. Okay, so I'll just say a bit about what we know, and I promise I'm wrapping up right now. A bit about what we know. Black people, Black Americans, are not getting very many bachelor's degrees in physics, which of course has a strong effect on representation at all the higher levels. And actually, if you look at this plot on the left, the average is going down. I mean, the sort of trajectory is downwards, right? So we have this problem where Black people are being increasingly decreasingly represented in physics. Right? This is another plot showing the actual number of PhDs awarded to Black Americans and Hispanic Americans. And we see that over the last couple of decades, this number has essentially remained flat, and it's in the tens, right? It's in the low tens. And really, I think, problematic fact is that I think it was just like a month ago, the 100th Black woman in the US ever to get her PhD in physics got her PhD in physics, right? These numbers are incredibly low, and we absolutely need to address them. Okay, so there's this really awesome report that came out from the American Institute of Physics Team Up Task Force, and they found 5 factors affecting Black American undergrads, right? This is a sense of belonging. This is something that I mentioned quite a bit. My sense of belonging was attacked a lot for a long time. And again, I almost convinced myself that I didn't belong in physics. And I'm glad that I had really important mentors to help pull me out of that. The sense of physics identity. Again, this is related to belonging, but it's just sort of like, do you really see this as something that you can do professionally? Not really sort of maybe a future projecting sort of way. Academic support is another item that the task force mentioned in the report. They found that students can be really negatively affected when deficit thinking, like applied to their involvement or like their goodness of fit, so to speak, is combined with the notion of an ideal meritocracy. When there's lots of evidence to say that our meritocracy is not so meritocratic as we think, say it that way. They also found that Black students often lack a certain personal support, and that it's exacerbated, like problems with this is exacerbated by faculty not being aware of resources for Black students, right? Especially as they relate to like racial harassment. For example, there's a Title IX office, right? But there's not a Title VI office where you can go and report grievances for racial harassment, right? And lastly, like leadership and structures, basically like there's just overall lack of department policies and enforcement of like norms and values that really foster a sense of inclusion and belonging. For Black students in particular, there's a lack of diverse faculty across the board, and representation really matters. It's very inspiring to see someone who has, gotten through the hurdles that you seek to get over. It really makes it seem like you can do it too. This is an important factor. Okay, and so my last point about this is at all levels in physics, Black physicists deal with isolation, persistent scrutiny and suspicion, fear of retribution for voicing concerns, and denial that bias and discrimination exists. And this forces a lot of Black physicists out. I say a lot about this in the Physicist A piece called Disentangling Anti-Blackness from Physics, if you want to learn more about this. One more comment, this has really profound impacts on the STEM workforce. All right, this is just a really quick plot showing who, like the ethnic demographics of who holds science and engineering positions generally. And we see that the demographics of white men and women take up a majority of this plot. I'm gonna, there are lots of marginalized people, but I tend to speak about Black people because I'm an expert on that. You see that Black people make up a small sliver. Okay, so just want to highlight that. And this relates to this last plot. I promise I'm done. This last plot of early career doctorate holders, ECDHs, which bring new skills and knowledge to the STEM workforce. And they're often drivers of the technological economy and knowledge generation. And we see that a large majority of these people are just from two demographics, white men and white women. Black men being the smallest of this demographic, right? This is, again, so this is a measurement of sort of who is represented, who is thinking of the problems, who is coming up with solutions to the problems. And it can tell you a lot about who is going to be left out of thinking, of being considered when people are coming up with solutions to problems, right? We have many important examples of this happening when it comes to simple stuff like going to the airport, and the fact that I can't always guarantee that when I stick my hands under the little sensor that's supposed to turn on the water that it works. It often doesn't. Or something like Fitbits. Like Fitbits cannot measure my heart rate because my skin is dark. There are more important examples of like artificial intelligence algorithms, machine learning that has bias coded into it that incorrectly will like pick out darker skinned people or people with certain facial features for whatever. And if you think about that being used as a way to like find criminals, right? Like this is, it's already becoming a really problematic thing. And so just, it's important that like we address this representation so that the technological solutions that we come up with aren't hurting people literally, but also we are very, STEM driven economy. And so to not have better representation across the board for these different ethnic demographics is to very significantly limit the socioeconomic mobility of a lot of these groups. This is really important for that, especially in this new dawn of quantum computing, right? People hear about quantum computing all the time. We need to make sure that lots of people are getting trained to be part of the budding quantum workforce. This is incredibly important because if they're not, a large number of people are going to get left behind. And we shouldn't let that happen. Okay, so I'm completely done. Here's some food for thought. Please read this. I will actually read it in case anyone is just listening and not watching. The second grade school teacher posed a simple enough problem to the class. Quote, there are 4 blackbirds sitting in a tree. You take a slingshot and shoot one of them. How many are left? 3, answered the first 7-year-old boy with certainty. 1 subtracted from 4 leaves 3. 0, answered the second 7-year-old boy with equal certainty. If you shoot one bird, the others will fly away. Author unknown. Thank you very much for listening to me and allowing me to go over. I'm happy to stay around and answer questions, have discussion for as long as we need to. Thank you.
Thank you so much, Charles. That was excellent. Thank you for sharing both your science, which was so interesting and wonderful to hear about, but also sharing about your journey, which, it's too few the opportunities to have people share their stories like that. So I think that was really excellent. So I know we're a little over, but I noticed already there are a couple questions in the chat. I don't know, Charles, if you can see the Q&A.
Oh, yes.
It
let's
looks
see.
like, oh, they're referencing plots from before.
Oh, I see. What created all the light? How fast is this? Okay, so let me just try to give a quick answer to these questions. One, I answer the easier of the two. What created all of the light? So the light that we use to make our lattices, it comes from almost one laser. We have this incredibly beefy laser that outputs 50 watts of laser light, 50 watts of laser light over like over a cross section of a millimeter. Right? This is a really, really small amount of space to have a lot of power. This is absolutely something that will burn your skin if you touch it. Like you stick your finger in it, your finger will smoke. You will have a terrible, terrible burn. We use a laser like that at 1064 nanometers, and we actually convert most of it into green light by sending it to a frequency doubling crystal. Right, so that's how we generate the green light and the infrared light that we use to make the Kagome lattice. Then we send them over to a different optical table where our atoms are. That's where that light comes from. The first question, this is what could be the reason for the lower quadrants having a spread on either side of the lowest point? Plot B4. I'm not entirely sure. Is the name Aminato? If you're on, could you ask me directly?
I'm not actually sure if participants are able to, I might be able to unmute.
Oh, I see.
I just allowed her to talk. So she should,
Great.
Amy, you can unmute yourself now.
Okay. Hi. Sorry.
Hi.
Can you hear me?
Yeah.
Hello. Yeah.
Hi.
Thank you. Really great talk, by the way. Really enjoyed it.
Thank you.
I was,
Thank you.
yeah, I was wondering about, it was when you were showing the models of how you expected, I guess when you were, it was back when you were talking about Bose-Einstein condensates, and then.
Yeah. Let me share my screen quickly, if that's okay. I suspect you are talking about.
Yes.
Is it this one?
Yep, that
Okay.
lower one. Yeah, the lower one in blue, with the blue peaks.
What's going on? The lower one. Sorry, I don't know what's going on with the PowerPoint. 1 second.
Oh yeah, no worries.
This one right here. You can see my mouse, right? This one.
Yeah, because every single one is pretty much perfect, except for well, you know, like pretty much spot on, and then this one is almost, except there's just this on the lower spot. They just spread out just a slightly, and I was just
Yeah. So what you're noticing, it's very astute of you to see this. This is a problem with how we put the atoms into the fourth energy band. So it turns out that when you're applying these forces to a Bose-Einstein condensate and you're trying to load them into a particular energy band, you have to be mindful of the energy associated with the difference between the ground band, the lowest band, and the band that you want to load them into. The gap is a band gap, and it's a certain energy. And if you give the atoms more than that energy, then what you've done is you've done a non-adiabatic ramp. And you might say in like quantum language, you've done non-adiabatic evolution of your quantum state. And what that means is you're not going to be very good at actually putting the atoms into the state that you want to. They're going to leak out into other states that you didn't mean for them to be in. And so the reason why this image doesn't look like, it doesn't quite look like the prediction above it, is because we weren't very adiabatic. We did the ramp too fast, too hard, and the states of the atoms, of some of the atoms, have gone into other states that we don't want them to be into.
Okay, thank you.
Yeah. So I'll just answer a couple more questions. I see there's some more in the.
Yeah.
Cool. So someone asked, can I mention the title of my publication on the diversity that you referenced? Yes. The title is Disentangling Anti-Blackness from Physics, and it was published in Physics Today. Let me also mention another publication. So as Alex mentioned, I was one of the lead organizers of Black in Physics Week, and for that week, we had 7 publications co-published by Physics Today and Physics Week. They are all really, really amazing. You should absolutely check them out. The last one I co-wrote with Jessica Esquivel. She is a postdoc at Fermilab. And in that article, we wrote about Black representation in artificial intelligence, in which she has expertise. She uses it for research. And I spoke about Black representation in quantum science, information science and engineering. So I would check that one out too. That one's called Part of the Revolution, Black representation in AI and quantum information science. But that one's in Physics Today and Physics World. Okay, Alex, is it okay if I just keep answering some questions? Yeah.
Yeah, it's fine by me if you don't mind.
Yeah, no problem. Let's see. Are there opportunities that could be created to have local students visit the lab with you? I thank you, Scott. I appreciate that you find that I would inspire students. I really, really do appreciate that. I think that there are probably opportunities. So we could definitely make it happen. My postdoc advisor, Dan Stamper-Kern, he's leading a very large effort with some other professors from California universities. As part of this NSF initiative, they're called Quantum Leap Challenge Institutes. And the goal is to use this ridiculous amount of funding and lots of different research resources to like make quantum computers more of a thing, and a real thing, I mean. And part of this endeavor is supposed to be education based, education focused. So I do think that there's actual like money available to definitely get research experiences, get internships, certainly to bring students in. I think that'd be easy to do. I would be happy to talk with you about doing this. We can talk about this via email for sure.
I guess I will.
Do you suggest?
I was going to say, I'll also mention, since we are over, I guess if people do need to leave, of course, people can leave, just so the audience knows. But I think, and I also want to be respectful of your time. But if you don't mind answering the questions
I don't mind.
Want to hear. Okay.
I don't mind. I'm the one that went over. So yes,
okay,
as Alex mentioned, if you need to leave, please, it's okay. I will not be offended. But I will answer some questions since I went over.
Cool. I'm interested in the answers, so that's great.
Awesome. Yeah, so someone asked, do I suggest going to Yale as a black, do you suggest going to Yale as a black student applying today? Yes, I do. This is a really good question. But yes, I think that like there are benefits to going to a PWI, primarily white institute, like Yale, to an Ivy. There's benefits to going to a HBCU. I think there are pros and cons of both. I think that you will have difficulties being a black person at Yale, but I think you'll have difficulties being a black person in the US more broadly. And I think that being a graduate student at Yale offered me a lot of really important opportunities that I wouldn't have got elsewhere. And so I think that if you go to a place like Yale and you make it a point to find community, find people who like really respect you and treat you like the scientist that you are, I think it would be okay. It won't always feel good, but overall, I think it would be okay, and perhaps even very good, very good. Another question about BECs, very nice. Yes, BECs are amazing. When it comes to the velocity of the BEC, how fast is it traveling, and how fast is the highest velocity produced? It's actually not moving very fast. The highest we make it go is about 5 millimeters per second to get it to the flat band, the third band, which is where we wanted to do our science. So pretty slowly. A question about my pre-college drive to go into STEM. Do you know how you started to get that drive? Do you have a source of information that helped show you it was possible? Did you get pushback on being in STEM back then? So a lot of that drive, it started with my mom. So my mom really she loves space. She loves space physics. She, in a different life, she would be an astrophysicist and she would be super content. She's a huge like sci-fi geek person. She loves like Star Wars and Star Trek. And I remember, she'd come home late at night from work and we would watch X-Files and eat Doritos with salsa. Like these are just random memories I have. So it was that, like, she was always watching sci-fi. She was always talking about sci-fi stuff, always talking about space, always wanted to take me to the science museum, always getting me science books to read from the library or just whatever. So it's just like this constant talk about science. And I think it got me really curious about how things work because, she was telling me all this wacky stuff about the world, about the universe. And, kids will ask you the most ridiculous and difficult questions, like not ridiculous in a bad way, like really, really good fundamental questions that you have no idea how to answer. And I did a lot of that and I got really curious about how stuff works. And so through that process, I figured out like, okay, I want to do science or something like that. I also really like building. I was all about Legos, built these huge structures in my room. I had these car tracks you can like stick together. And I'd make these gigantic things that take up my whole room. And I just like send marbles through them and they go all around the room. I tried to build a lab in my mom's garage. I tried to build a laser, it didn't work. I mean, I was always like building stuff with my hands. And yeah, I guess just through all of that, I just like sort of knew like, okay, this is what I'm meant to do. This is what I was passionate about. That's sort of where it came from. It didn't come from a lot of like knowing how to make this a real thing. I think like, how did this happen for me? A lot of luck, a lot of drive from my mom, I'll say luck again, a lot of good fortune and persistence. I work really hard. I'm really passionate about science. That's what made it happen. But I think I absolutely made a lot of mistakes along the way, which is, part of the reason why it took me 6 years to get my bachelor's, which is okay. It's okay if it takes longer, but for me, it took 6 years because I made some important and costly mistakes. Yeah, I think that's what I have to say about that.
All right, well, it looks like that might have been our last question. So if there aren't any other ones, let's thank Dr. Brown again, or I guess you can't see everyone else clapping, but I'll clap on behalf of everyone.
Thank you. Thank you.
So thank you so much. That was excellent. And thank you everyone for coming. And I hope you come to our future Science by Diverse Scientists talks. So thank you, everyone. Thanks.
All right. Thank you. Thank you very much for having me.